Okay, hi everyone. This is lecture 31 on my series on algebraic number theory. And today we're going to be talking about some of the preliminaries you need in order to define the class group of a number field. So our goal is to define the class group of a Dedekind domain, and this is going to give us a useful invariant for Dedekind domains and in particular for number fields. So the overview of what we're going to talk about today. First, we're going to talk about something called a fractional ideal. Okay. We're going to talk about the fact that containment of these fractional ideals is equivalent to division. So I'll be more specific about what this means when we get there. We're going to show that every ideal divides a principal ideal. And then we're finally going to define what the ideal class group is. Okay. So I'll start with this definition of a fractional ideal, and these are going to form basically the elements of our group. So I'm going to let A be a Dedekind domain. And let's say I have a field of fractions K. An A module so an A submodule of K is a fractional ideal if all the elements of M have some common denominator. So if dm is contained in A for some non-zero d in A. Okay, so you can basically think about these as taking an ideal from A and then dividing by some fixed denominator, more or less. And so the main result that we're going to show in the next few lectures is that if I define this guy, the ideal class group of my Dedekind domain A, which is basically just the set of fractional ideals. But this actually has a group structure. It's an abelian group freely generated by the prime ideals of A. So the main difficulty, so that there's going to be an operation which is basically just take the product of two modules. The main challenge is showing that ideals have inverses, and that's going to be basically the the extent of 2 and 3 here. Prime ideals. And then we'll prove this free on the prime ideals of A fact later. Okay. And so the strategy for proving that ideals have inverses is to basically reduce to the principal ideal case. So I'm going to show that every ideal divides a principal ideal, and then I'm going to invert that principal ideal, which is then going to allow me to invert my original ideal. Something like this. Okay. So the next thing I want to show is the following proposition. I'm going to let A and B be ideals. Okay. And so we say, so I guess there's like a little definition rolled up in here. We say A divides B if there exists an ideal C subset of A. And I should say this is an ideal such that my ideal A times my ideal C equals B. Okay, and so the claim, so with this definition of divides in mind, I claim, I guess, A divides B if and only if we have containment of ideals, if only if A contains B. Okay, so one direction is not too bad. Every element of this product of two ideals is going to be contained in A, so if A times C equals B, then B has to be contained in A. So, proof. Since A times C is contained in A, if A times C equals B, then B is also contained in A. So the other direction is the hard part. Now suppose we have containment. And the idea is to use our unique factorization of ideals in order to kind of think about what B could possibly be and find a divisor C. Now suppose A contains B. So I'm going to let A be the following product of prime ideals. And I'm going to let B be the following product of prime ideals. And so I can choose the same prime ideals here as long as I let the powers possibly be 0 initially. Yeah. So I'm only using the fact that A and B factor into product of prime ideals. Okay, so yeah, basically if a prime of A does not divide B, we just tack it on with the power of 0. And similarly, if a prime of B does not divide A, then we just tack it on with the power of 0. Okay, so we need to recall something about the structure of the local rings in this case. That the power here is basically determined by the ideal A generates in the localization. Okay. And the same is true for B. Okay, so if I want to determine the power, I basically look at the localization, the ideals these things generate in the localization at that prime. Okay, and since A contains B, the ideal A generates in the localization at Pi contains the ideal B generates in the localization at Pi. So basically each EI has to be less than or equal to each FI. Okay. Based on the properties of ideals in local rings. Okay. Here we use the structure, I guess, of ideals in, I guess maybe not just a local ring, but a DVR. So recall, A is a Dedekind domain. This means that each localization here is a DVR, and basically there's a chain of ideals, a unique chain of ideals in this DVR, which looks like powers of the prime. Okay, and then basically I just let C be P1 to the E1 minus F1, PR to the ER minus FR. Okay, and since all these are non-negative, this will be an ideal in A. And you can easily check that this C satisfies the condition that A times C equals B. Okay, so this is basically shows that if my ideal contains another ideal, then it also divides it in this sense. So we immediately get a corollary, which is that every ideal divides a principal ideal. 31.3 corollary. Given an ideal A, it necessarily divides a principal ideal. Yeah, I guess what I really want is, given a non-zero ideal A, it necessarily divides a non-zero principal ideal. Okay. Proof. So this follows basically immediately from 31.2. Since A is non-zero, it contains a non-zero element. It's going to contain the ideal generated by that, and by 31.2, the proposition we just proved, A divides this ideal generated by alpha. Okay, so with this corollary, we can actually show that our thing we wrote up here forms an abelian group. Okay. So that'll be the main theorem from this lecture. 31.4 theorem. Let A be a Dedekind domain. and we're going to let the ideal class group of A, or I guess this should just be the ideal group of A. I don't know why I keep calling it the ideal class group. We're going to take a quotient of this, and that will be the ideal class group. Or just the class group most of the time. Okay, so these are going to be the collection of fractional ideals. So the collection of finitely generated submodules. Or, yeah, I guess it turns out that's equivalent, but we'll use our definition from earlier. Collection of M, a fractional ideal. Okay. Then this forms a group where the product operation is defined as follows. M times N, the set of sums. It's a set of sums of products of elements. So basically just the product operation for ideals generalized to submodules of the fraction field. Okay. And I guess we'll also prove the fact that it's free on the prime ideals. Furthermore, this is a free abelian group. Generated by prime ideals. So first, yes, let's go ahead and prove this. Basically, first I'm going to note that this set ID of A is closed under multiplication. If A times M is contained in A, and I have B times N is contained in A, then you can pretty quickly check that A times B times M times N is also contained in A. Thus, ID A is closed under our group operation. Basically, we have a well-defined operation on our hands. Okay. The commutativity of the group operation follows basically immediately from the fact that multiplication in K is commutative. Okay. So we need to show, basically, we have an identity element, we have inverses, and I guess I should remark that basically the same is true for associativity. If you want, you can check it by hand, but it basically just boils down to the fact that multiplication in K is associative. Okay. So what we really want to show is that we have inverses. The identity element is just the module A. To see this, basically just note that since M is an A module, A times M is contained in M, and since 1 is in A, M, which equals 1 times M, is contained in A times M. Okay, so these two have to be equal. So the identity element is A. What we really again want to show is that elements have inverses. First note for D not equal to 0 in A, if I take the ideal generated, I guess what do I mean by this? I take the A module generated by 1 over D. This is a fractional ideal. Okay. So we see that D times 1 over D equals A. Hence, principal ideals in A these have inverses. So basically, if I can multiply something to get multiply by something to get a principal ideal in A, then we're kind of in business. We're pretty much done. So we're going to let M be a fractional ideal. Such that, let's say I know the element D times M is contained in A. Okay. This collection D times M will be an ideal in A. And hence will divide a principal ideal by the previous corollary. Okay. What does this mean? Basically it means there exists an ideal A contained in A such that the ideal generated by D times M times A, let's say, is the principal ideal generated by alpha. Then M inverse is just going to be the ideal generated by 1 over alpha, the ideal generated by D times A. Okay, and since each of these, this is an ideal in A and this is an ideal in A. Ideals in A are fractional ideals. You can just take D equals 1 if you like in the definition. And this is also a fractional ideal, as we just kind of checked. So this product of fractional ideals is again a fractional ideal. So this is the inverse. Okay. So this is how you show that M is, or that the collection of fractional ideals forms an abelian group. Next, we want to check this claim about being free. Okay. So next I claim DA is freely generated by prime ideals of A. Okay, so we're going to let M be a fractional ideal. So first we're going to show generation. And let's say I know that I've got some guy D, which puts me in A. Then by the unique factorization of ideals in A, I can factor D as P1 to the E1, PR to the ER. And since this guy is an ideal in A, I can also factor him. Say this is equal to Q1 to the F1 times QS to the FS. And this is for some prime ideals PI and QI contained in A. And here I can just assume the EI and FI are greater than 0. Okay. Finally, we can see that M is basically just multiplied by D inverse. So we invert all these primes. It's going to be Q1 F1 QS FS and then P1 E1 PR ER inverse. Okay, and this is in the group generated by prime ideals. Okay, so this shows generation. Now we need to show basically linear independence of prime ideals, that this is freely generated. Okay. So suppose basically I've got something like this. I've got some product of prime ideals equaling the identity. And I'm going to split them up based on the powers that are non-negative and the powers that are negative. Okay. With EI greater than or equal to 0 and FI less than 0. And so we can always split this product up in this way. Basically, I'm grouping the positive terms together and the negative terms together. And what we're going to see is we'll have the equality of two ideals in A. This guy is going to be equal to this guy, just multiplying by the inverse of this tail end expression. And so by the unique factorization of ideals, we have basically that these guys are some rearrangement of these guys with the same power. And we can assume without loss of generality just by reordering our lists. That P R plus I equals PI and FI equals EI. Okay. So tells me that basically that all this is that each power of the PI's is 0. Each power of PI in, I guess this should be negative here. Each power of PI in this guy is 0. And this shows linear independence. Okay, this is probably not the best way to explain this. I should have maybe assumed that each PI here is independent, something like this. Like they're all distinct. And then you would like basically immediately run into a contradiction down here, but this also works. And we've shown independence, so we showed generation, we shown independence, and that proves the group of fractional ideals is free on the prime ideals of A. Okay, finally I can define the ideal class group. 31.5 definition. Okay. So I'm going to let A be a Dedekind domain. I could define the subgroup of principal fractional ideals and typically you'll write this P of A and it sits inside id A. These are just the ideals generated by elements of the non-zero elements of the fraction field. Okay, and then the ideal class group. Ideals. And the class group of A is denoted something like this. CL of A is the quotient. Okay, so it's all fractional ideals modulo principal fractional ideals. And over the next few lectures, probably several lectures, we'll show that this is actually a finite group in the case that A is a number field. Okay, so that's the preliminaries for the class group, and we finally got to define the thing.